this is Carter, and this is part 2 of my particle motion review. In my last review, I went over a lot of the basic concepts of particle motion that we are going to see on the AP Calculus BC and AP Calculus AB for responses. So if you haven't checked that out, I suggest that you go and view that. So in this video, I am going to go over a few more of these particle motion concepts that we often see tested on the AP Calculus FRQ. The first of these concepts being, is a particle moving toward or away from the origin? And as we will see, this will depend on the particle's position and velocity, specifically what the signs of the position and velocity are. So let's look at a few scenarios of this. Let's say that we have a particle with a positive position and a positive velocity. So since it is a positive position, we know it's going to start out to the right of the origin. And since it has a positive velocity, that means the position is increasing, it will be moving to the right. And as we can see here, this particle, since it is starting out to the right and it is continuing to move to the right of the origin, it is moving away from the origin. Okay, now, what if a particle has a negative position and a negative velocity? Well, since it is a negative position, it will start out to the left of the origin. And since it has a negative velocity, it will move to the left. So it is starting out to the left of the origin and it is continuing to move left. So it is moving away from the origin. Okay, now, what if a particle has a positive position and a negative velocity? So since it has a positive position, it will be starting out to the right of the origin, and since it is a negative velocity, it will be moving to the left. So as we can see, this is moving toward the origin. And lastly, if a particle has a negative position and a positive velocity, it will start out to the left of the origin because of its negative position, and since its velocity is positive, it will move to the right. So it is starting out to the left of the origin, it is moving left, so therefore we know it is moving toward origin. So let's think about the conclusion we can come to after looking at these four scenarios. Well, let's see. In conclusion, we know that when a particle's position and velocity have the same signs, it is moving away from the origin. We can see this in the first two examples. Both of these have the same signs in both of these scenarios. The first scenario, they both have positive signs, and in the second scenario, they both have negative signs. And in both of these, it is moving away from the origin because it is simply starting, let's say here, it is starting to the right, it is continuing to move to the right, and here it is starting to the left, and it is continuing to move to the left. So it is moving away from the origin. And then the other conclusion we can come to is that when a particle's position and velocity have opposite signs, it is moving toward the origin. And we can see this in the last two scenarios. When they have opposite signs, it is starting out to one side of the origin, like in the first one, it is starting out to the right of the origin, and it is moving the opposite direction. So it would be moving toward the origin. So let's say we have a problem, and at, 1 second, position is at 5, and at 1 second, velocity is at 2. If it asks us, is the particle moving toward or away from the origin, we can just draw this number line. We know position is to the right of the origin because it is positive, and we know it will continue to move to the right because velocity is positive. So our explanation for this can just be, because they're going to want an explanation on these FRQs, it will just say away from the origin because the particle's position and velocity have the same sign. That is all the explanation that you need. And if they had opposite signs, you could say it is moving toward the origin because they have opposite signs. Okay, this next concept I want to go over is oftentimes in these FRQs, it will give you a particle's position at a certain point, and then it will give you its velocity graph or function, and it's going to ask you to find the particle's position at a certain point. Well, let's think back to the fundamental theorem of calculus. Because of the fundamental theorem of calculus, we know that displacement, otherwise known as x at its end time minus x at its initial time, that equals x, well, x being position, that equals the integral of velocity from a to b. So the integral of velocity from a to b is simply a particle's displacement. And since it is the integral of velocity from a to b, it is simply accumulating its velocity, and that is its displacement. So we can just use simple algebra to rewrite this equation as this. Final position equals starting position plus displacement. And this makes sense because let's think about it. If I start out at 3 meters away from the stop sign, and then I move 6 meters away from the stop sign in a certain amount of time, that is my displacement, 6 meters away from the stop sign. Then my initial, which was 3 meters away from the stop sign, plus 6, my displacement, that equals my final position, which would be 9. So let's think about this. If we're given a velocity and a position. So a particle has a velocity function of 2, and it has a position at 1, and that is 2. Find x at 4. Well, let's think about this. Let's just set up this equation. So we're trying to find x at time 4, and this would equal x at time 1, which is our starting, plus our displacement, which would be the integral of velocity from 1 to 4. Our lower bound is our starting position, and our upper bound is our final position. So we know what x at 1 is. We know they gave it to us. That is 2. Plus the integral of velocity from 1 to 4. And we can just find the area under the curve. That is what this area of the yellow region represents on this velocity graph. Since the integral is the area under the curve, we are finding the area under this curve of 2 from 1 to 4. So let's find this area. It's simply a rectangle. We are multiplying 2 meters per second, because that is this length, times 3 seconds. We can write that over 1. So we have 2 meters per second times 3 seconds. And these seconds cancel out, so our displacement is simply 6 meters. So our displacement, our position is 2 meters plus 6 meters. So x of 4 is 8 meters, or simply 8. So the answer would be x at time 4 equals 8. And now let's think about this again. If we rewrite this equation, in some scenarios, they're not always going to give us the starting position and have us find the final position. Sometimes they're going to want us to find the starting position using the final position in a velocity function. So we can rewrite this equation that we were just talking about as this equation. We can just move the integral of velocity to the other side, so that starting position equals final position minus some displacement. This makes sense. Our final position minus the displacement that got the particle to the final position equals the starting position. So let's say, just like this last problem, well, let's just change it around. Let's say we're given the final position, which we found to be 8. Let's say they tell us that, and then they give us this velocity function. We can just do x of 4 minus the integral of velocity from 4 to 1 dt. And we know that that equals 6. And we know that this equals 8. So 8 minus 6, and that equals 2. Which is what we were given in the first place. So this is the formula. We can use this formula when they give us a final position and the velocity graph. And this formula is the formula that we can use when we are given the starting position and its velocity graph, and we are trying to find the final position. Okay, that's all I'm going to go over. Thank you, guys.